episode of Remote Linear Algebra, we will be looking at an example of a dynamical system and how you can use diagonal matrices to solve the system. This is more about the theory behind the programming and not about a practical way to do the problem. If you were just given this problem as a student, putting the matrices in your calculator and running the program on your calculator would be the most efficient way to number crunch an answer. But you're in linear algebra to learn the background and theoretical ideas behind the programming. You want to be able to understand the programming so that you could someday be one of the programmers. So we're going to look at this problem from the point of view of using diagonal matrices. So we've seen this problem before if you've been in our class. The population of people in a town has remained steady for many years. Given recent months, 44% of the population who had taken up Pokemon Go as a form of recreation have quit playing. That means 56% are still playing. 26% of the population who previously did not play Pokemon Go end up taking up playing. That means 74% of the population did not take up playing if they weren't already playing. Set up a matrix system to calculate the number of people who play Pokemon Go this month and how many do not play this month if last month 118,000 people played Pokemon Go and 84,000 people did not in this town's population. Then we're going to use the system to estimate the number of people who will play Pokemon Go in 6 months, but we're going to look at it from the point of view of diagonal matrices. So let's remember the percentages. 44% currently playing quit. That means 56% currently playing stay playing. 26% who previously did not play, meaning 74% who did not play still don't play. And then we have these numbers from last month in the population. So our dynamical system matrix is 0.56 for 56% of the people still play if they were currently playing, and 26% who did not play take up playing. So we're going to have X, the first variable, be people who play. So X will be people who play. And then Y, the second variable, will be people who do not play. You know, either they quit or they never took it up. So 44% of the people who were playing quit playing, and 74% of the people who never played still don't play. So that's where these values are coming from. Then we want to build our diagonal matrix. And so remember from earlier videos that the diagonal matrix is based on the eigenvalues of a matrix, and to get the eigenvalues we have to form the characteristic equation. So the characteristic equation comes from taking the determinant of this form and setting that determinant equal to 0. Again, the other video explains, why this is. We want this determinant to equal 0 so that we are guaranteed non-trivial solutions. So for a 2x2, the determinant is the cross products, the difference between the cross products. So I multiply these two binomials and then I subtract those two decimals. And if I clean it up, I get lambda squared minus 1.3 lambda plus 0.3 lambda, again, equals 0. That's from the equals 0 for the determinant equation. And if you solve that, the two zeros are 1 and 0.3. So my diagonal matrix is 1 and 0.3 down the diagonal and zeros everywhere else. So that's my diagonal matrix. Then to finish building the system, we need to find that other matrix that is often called P that works in concert with D to equal our original dynamical system matrix. So I want to RREF 0.56 minus the first eigenvalue, and then in the diagonal I also subtract that first eigenvalue, and I leave these other two values the same, and I do the reduced row echelon form on that, and this is what we end up with as the RREF form, and that gives us a solution for a basis vector of x equals 13 over 22 times y. If you let y be 22, then x would have to be 13. So I could use this as a eigenbasis vector for the eigenvalue lambda equals 1. I also could have used 1 for y and the fraction 13/22 for x. I just decided to work with whole numbers. And then we'll do the same for the 0.3. You take the diagonal and subtract 0.3. Again, the theory behind this is in the earlier videos about eigenvalues and characteristic matrices and the diagonal matrix. So if you kind of went through those videos, you'd kind of see the background information about why we're doing what we're doing. So if I take the row reduced form of this, I get this simple matrix 1, 1, 0, 0. Reading that first line, x plus y would have to be 0, meaning x would have to be the opposite of y. That gives this as an eigenbasis vector for lambda equals 0.3. All right, now that I have all of those pieces, I can build this product of matrices that is equivalent to my original matrix raised to the 6th power, because we're going to end up, remember we had to first form the system, so this would be what you would use for just 1 month, but then we wanted to continue the process and see what would happen if you continued this same process with these same percentages 6 months out. So that's why we have the power of 6. So P is built out of the eigenbasis vector. So this is the eigenbasis vector for lambda 1. This is the eigenbasis vector for 0.3. This is my diagonal matrix raised to the 6th power to answer for 6 months out. And then we multiply by P inverse. Now we're going to apply our original population values. So these were the values from last month. Again, if I had just multiplied those by my original dynamical system, that would have given me for this current month. We're now predicting for 6 months out. So if you calculate this, notice that when I raise this matrix to the 6th power, I only have to raise the values on the diagonal. And 1 to the 6th power is just 1. And so 0.3 to the 6th power is a little messier, but considering the other values are 0, finding this to the 6th power is very clean. So it's going to take your calculator or a computer less steps to calculate this to the 6th power than if we used the original matrix. And it raised to the 6th power multiplied by these P and P inverse in the order that we have them will give us an equivalent matrix to A to the 6th power, A being our original dynamical system. Then multiply that by my original population values, and I get around 75,060 people are still playing in 6 months. 126,940 people are not playing in 6 months. So that's a nice example just of a 2x2 showing a dynamical system. By the way, in our class we're not going to necessarily get into this, but there can be complex eigenvalues, and a place where they show up is sometimes in analysis of dynamical systems. Periodic systems, systems that repeat, rotations, those are also places that use complex eigenvalues. So here's a little graph showing a rotation and repeated solutions, and those kinds of systems will involve complex eigenvalues. So I just kind of wanted to mention that there can be complex eigenvalues, and they do show up in more involved problems than the one that we went over. But dynamical systems is one of the places where you might run across complex eigenvalues.